Example 1. Weights of Army personnel. Listed below are weights of randomly selected male U.S. Army personnel from dataset 2, answer 1, 1988, and dataset 3, answer 2, 2012. We want to use a 0.05 significance level to test the claim that the variation among weights did not change from the answer 1 study in 1988 to the answer 2 study in 2012. So the first thing we want to do is we want to be able to use StatCrunch to find the following. We want to find out what is the value of n, meaning the sample size for both. We want to be able to find the sample standard deviation, and then what is the variance. So what we're going to do is we're going to open up StatCrunch. We're going to put in our values. So if you see here in column 1, I put in the title and then put in the values here, and then the second column here. So we're going to go to Stat. We're going to go to Summary Stats and then select Columns. So I'm going to go ahead and select both columns. Okay. And I just want to get the n and the standard deviation. So we're going to see what the variance looks like. So I'm just going to do the value of n and the standard deviation. So I'm going to go ahead and select Compute. Okay, so now I have my summary statistics. I'm going to go ahead and use that information. Okay, so let's take a look here. So for answer 1, 1988, n is equal to 12. We have the sample standard deviation to be 12.419401, and therefore the variance will be that standard deviation squared. So we're not going to go ahead and evaluate that. We're just going to say that this is the number squared. That's the variance. Now for answer 2, 2012, we can see that the sample size n is 10. The sample standard deviation is 15.530629 kilograms there. And then the variance is that number squared. So when you're looking at that, we have to decide which one is larger. Well, we know that 15 is larger than 12, so the variance for answer 2012 is going to have the larger variance. So now we need to determine that. So because we stipulate that the larger variance is denoted by s subscript 1 squared, then what we're going to do now is switch the above two data sets, and we're going to let the variance 1 equal 15.530629 squared, and n1 is going to equal 10, and then by default the sample variance 2 is 12.419401 squared, and n2 is equal to 12. So again, let's just take a look at that. We know that this represents the larger variance, so we're going to call it s subscript 1. Therefore, that's how we get the sample variance, and sample size 1 is equal to 10. And then by default, we know that this is going to represent sample variance 2 with the sample size being 12. Okay, so that's the first thing that we need to do. Therefore, now we know that answer 2, 2012, is going to represent population variance 1, and we're going to let answer 1, 1988, be population variance 2. Now we can go ahead and then look at the requirements. Number 1, the two populations are independent of each other, and the two samples are not matched in any way. And number 2, given the design for the study, we assume that the two samples can be treated as simple random samples. And number 3, a normal quantile plot of each set of sample weights is going to show that both samples appear to be from populations with a normal distribution. So let's go ahead and do that. So we're going to go ahead and come in here, and we want to find the QQ plot for both of them. So we're going to go to Graph, come down here for QQ plot, and then select both of them. Make sure the horizontal lines are checked and the vertical lines are checked. So here is answer 1. So let's go ahead and take a look at that graph. And then scroll to the right. And then now we're looking at the answer 2 graph. So let's take a look at those two. Now we can confirm what those graphs look like. And so as we can see that they both represent a normal distribution. So here are our two graphs, And you can see that it represents a normal distribution. So therefore, the requirements are satisfied. Okay, now we're going to state the claim and the opposite of the claim. Okay, now the claim is that the variation did not change from answer 1, 1988 to answer 2, 2012. Now, again, recall that we're letting answer 2 be population standard deviation 1. So let's go ahead and then just copy this so that we know that this is how we're setting up the following. So the claim is that population standard deviation 1 is equal to population variance 2. And the opposite of the claim is that population variance 1 is not equal to population variance 2. So we know that the equality is always going to go with the null hypothesis, and therefore we would state that the opposite is now going to be the alternative. So we would identify the null and the alternative hypothesis. So the null hypothesis is that answer 2, 2012 population variance is equal to answer 1, 1988 population variance. And then the null is that population variance 1 is not equal to population variance 2. So now we're going to use the alternative hypothesis to determine whether it is a left, right, or two-tailed distribution. Now this is a two-tailed distribution since the alternative hypothesis contains the not equal sign. Then we're going to select the significance level alpha. Well, in the problem, alpha is equal to 0.05. And now in step 7, we want to find the test statistic for the hypothesis test with two variances, with the null hypothesis being population variance 1 equal to population variance 2. So recall that sample variance 1 is 15.530629 squared, and sample variance 2 is 12.419401 squared. So the F test statistic is sample variance 1 divided by sample variance 2. So we're taking that value and then dividing it by that value. And let's just go ahead and do that on our calculator just to make sure that we get that correct value. So if we do the following, we have 15.530629 squared, and then divide that by 12.419401 squared. Well, that gives us 1.563784092, which then gives us approximately 1.5638. And so therefore that gives us our test statistic. Now we need to find the degrees of freedom. Now for the degrees of freedom, we know that the numerator degrees of freedom for the sample size 1 is 10. Therefore 10 minus 1 is going to equal 9. And then for the denominator degrees of freedom, the sample size is 12. So 12 minus 1 is going to equal 11. So we can then determine what is the critical value. So now what we're going to do is move on to step 9. Okay, we're going to first draw the curve and then label using the p-value method. So again, we determine that the numerator degrees of freedom is 10 minus 1, which is 9. The denominator degrees of freedom is 12 minus 1, which is 11. And the test statistic that we found in step 7 is 1.5638. So now let's go ahead and then draw our bell curve. Now recall here that this distribution is going to start at 0, and it's going to have a right tail distribution. Okay, and what do we know? We know that this test statistic is 1.5638. And so what we're interested in is this tail over here. And now keep in mind this is a two-tailed distribution. And since it's a two-tailed distribution, we're going to multiply that p-value by 2. So we're going to take 2 and then multiply by the p-value. So that's going to equal 2 times the f test statistic where it is greater than 1.5638. So let's go ahead and open up StatCrunch. So when we open up StatCrunch, we're now going to go ahead and then select Stat, and then we're going to go to Calculators, and then we're going to scroll all the way down where you see F, which represents the F test statistic or the F distribution. We're going to open that up. Okay, so now we need to put in the degrees, the numerator degrees of freedom, and we found that to be 9. So that's going to be 9. And then the denominator degrees of freedom is 11. And now what we're going to do is we want to find, this is to the right, so we want to make sure it's greater than. And then we're going to put in our test statistic of 1.5638. And so therefore, we end up getting 0.2389. So it's 2 times, again, that is 2389. So 0.2389. Okay? So down here, we can say the following. The p-value is therefore 2 times 0.2389, and we multiply it by 2. We get a p-value of 0.4778. So we're going to make a decision. Now, if we reject the null, if the p-value is less than or equal to the significance level alpha, we fail to reject the null hypothesis if the p-value is greater than the significance level alpha. Well, compare the p-value versus alpha. We saw that the p-value is 0.4778. which is greater than 0.05. Therefore, we fail to reject the null hypothesis. Okay, now let's go ahead and then do the critical value method. So the critical value method is the following. Well, again, we need to know what the numerator degrees of freedom is, which is 10 minus 1, which is 9. We also know the denominator degrees of freedom is 11. Okay, and we also know that the test statistic is 1.5638. So now we want to be able to find the lower and upper critical values for the two-tailed distribution. Okay, so what we need to find is alpha. We know alpha is 0.05, and we need to take 0.05 and divide by 2. And that's going to equal 0.025. So basically what they're saying here is the following. Okay, we're going to have this distribution that's right-tailed. Okay, and that means that we're going to have a lower critical value and we're going to have an upper critical value. Okay, and what else do we know? Well, we know that these areas are going to represent the critical regions. Okay, so we have a critical region here, and that is 0.025. And then over here, we also have a critical region, which is also 0.025. So if we want to find the lower, we're going to have to make sure that this area to the left is 0.025, and to find the upper critical value, it's going to be 0.025 to the right. So let's go ahead again and then open up StatCrunch. Now I'm going to keep this calculator open for the F calculator. I'm just going to go ahead and refresh. Okay, so Again, we know that the numerator degrees of freedom is 9. We know the denominator degrees of freedom is 11. And then for the lower, we're going to put less than or equal to, because we want this area, and we're going to put in 0.025. Select compute. And so therefore we get the following. So we get 0.2556. So for the lower, or the F lower, it's 0.2556. So let's go ahead and put that lower value in. So here, this is 0.2556. Okay, now we want to be able to find the upper critical value. So now what we're going to do is, again, just refresh. Okay, put in the value of 9 for the degrees of freedom in the numerator, and then 11 for the degrees of freedom in the denominator. And now we're going to change this to be greater than or equal to. And now we're going to put in 0.025 now on this side. And so now we get 3.5879 if we run it to 4 decimal places. So therefore now we get the critical value of 3.5879. Okay, now we're going to come back and now take a look at this test statistic, which is not T. Let me make sure that that's changed to F. So I'm going to make this correction here, and this should also be F. So the F test statistic, okay, is located somewhere in between here. This is the test statistic of 1.5638. So we can see that it's in between, but not in those critical regions. So now we reject the null hypothesis if the test statistic is in the critical region, and then we fail to reject the null hypothesis if the test statistic is not in the critical region. Now, since the test statistic of 1.5638 is not in the critical region, then we fail to reject the null hypothesis. So now we're going to state the conclusion. Now, going back up to the claim, okay, the claim shows equality, and we failed to reject the null hypothesis. So we're going to come down here to the very end, and then we're going to choose the following. At the very end here, it says the original claim does include equality, and we failed to reject the null hypothesis. So we're going to say that there is not sufficient evidence to warrant rejection the claim that, followed by the original claim. So now we would say that there is not sufficient evidence to warrant rejection of the claim that the two standard deviations are equal. So it appears that the variation among weights of male U.S. Army personnel did not change from 1988 to 2012. Now there are some alternative methods that we're not going to be doing here, but some of them are called the Count 5 method, which is a relatively simple alternative to the F test, and it does not require normally distributed populations. If the two sample sizes are equal, and if one sample has at least 5 of the largest mean absolute value deviations, then we conclude that the population has a larger variance. And then the other one is the Levine-Brown-Forsyth test. It's another alternative to the F test. It begins with the transformation of each of the sample values within the first sample, replace each x value within the absolute value of the median there, x minus the median, and then apply the same transformation to the second sample. So using the transform values, conduct a t-test of equality of means for independent samples, and because the transform values are now deviations, the t-test for equality of means is actually a test comparing variation in the two samples.